Okay, so this video is about binary search in a sorted rotated array. The sorted rotated array is array that have a pivot somewhere between the first element and the end element, such that it splits array into two halves. So this element, let's assume we have a positive sorted array. So in that case, we have some starting number. Our array grows like that, and then it reaches maximum, and then there is the next element, which is minimum, and from that array starts growing again and reaches final end element, last element, which is lower or equal than the first element. So obviously, before we start, we need to check that. We will have the very first check is the sanity check. We do comparison. So let's say we have array nums, which is rotated and which has elements 4, 7, 10, then 1 and 3. So the very first check we do, we compare the first element and the last element, and if the last element is greater than the first element, that means that we don't have a rotated array. So this is maybe just because we have only one element, or we have two elements and the second element is lower than the first element, or for whatever reason. Okay, so we do that check. If nums 0 is less than nums -1, we return and here's the question what we need to return. So there are two types of the problem solution sorted array. One is just to find a minimum or maximum. From that, like these pivot elements. So this one type of binary search and sorted array problem. And the second type of binary search array problem is where we need to find a index of a target element, target index. So in that case, what I want to do is to this particular case, when we have a case the first element lower than the last element, in that case we probably just have a sorted array. In that case, what we do is just do a binary search over nums, we pass the target, and we pass a first element as the left boundary and the last element as the right boundary. If you don't know what binary search algorithm is or how it works, I recorded a video previously which explained this in very detail. Okay, so second case, if it is not the true, that means that we have this case. So the last element is lower than the first element, or they're equal. There is both possibility. However, let's assume for the moment that we have a array which has no repeating elements. Right, so in that case, our algorithm has two parts. First, we need to find a pivot element. We need to find either max or min. They are consecutive, and from that we will check that if our target is greater than the first element, equal greater than the first element, then what we need to do is to apply binary search to the first half. If or first part, if target is not the equal or greater of the first element, then it means that it is somewhere in the right part, second part, and we just need to perform binary search at this part. If any of these binary searches doesn't find the target, that means the target doesn't exist in the array, and we return -1. So the time complexity of this approach will be initial binary search of the pivot, which is O log n, and also the plus the second search for the target in the in one of the parts. It will be also O log n, and yeah, so we can simplify it just O log n. Okay, so let's break it apart and let's go into details for the first part. So the first part is we need to find a pivot element, and we also use the approach similar to binary search with a little bit of caveat. So we define L and R equal to 0 and last element, which is nums -1, and we perform search while L is less or equal than R in the following. So first, of course, we take the middle element, which is L plus R divided by 2. So let's visualize array one more time. So this is L, this is R. So we pick elements. Then there are three cases. One first case is element either here or here. So the middle element is pointing to the either max or min. How we can check that? So we can check it if minimum, if nums m is greater than nums m plus 1, that means that m is pointing right here. So the next element is lower. That means that we found the pivot element. So let's assume we want to actually consider pivot as the maximum element. yeah, so let's for simplicity consider pivot as a maximum element. So in that case, if we found that nums of m greater than nums m plus 1, and for that also what we need to do is to do a sanity check where we check that actually m is less than r, and what this does is we're gonna rewrite as m plus 1 is less than or equal than r. What it does, it checks that we won't actually start comparing the last element with the non-existing element after the last. Right, so in this particular case we need to return m, this guy. So it's not the case if elif the and now we are checking that we are here, if we are here. So for that check we need to check that actually L is less or equal than m minus 1 because we want to check the previous element, and nums m minus 1 is greater than current nums m. Alright, so in that case we need to return, obviously this is m, in this case this is m minus 1. In that case we return m minus 1 as the maximum element. Right, so we covered this first case, case 1, and now let's check the second case. The second case is where the element is between the L and M. Okay, so in that case, how we can actually check that? We don't know yet where it is. In that case, actually, yeah, so we the way we can check that actually is to consider, so like again, so m could be here or it could be here. So how do we know where it is? For that, what we need to do is just to compare with the first element actually. So the m's element, so let's think about it. If in the first case m's element is here, so what did it tell us? That m's element is the greater or equal than the first element here. So let's check it. L if nums 0 is less or equal than nums m. Okay, so if it is here in this part is greater or equal to the first element, what do we do? So in that case we know that our pivot actually is somewhere in this part, and what we need to do is to move our left boundary just after the m right here. So in that case we assign L is equal to m plus 1. Alright, so what happens, like what's left? So the left, the only possibility is that our element is somewhere in this part. What happens if it is in this part? It means that we need to look for a pivot to the left of the m. In that case we need to move our right boundary to the element just before the m. Let's do that. R is equal to m minus 1. Right, so this is the procedure to find a pivot, and at the end we just return minus 1, and we return it. Actually, we don't return minus 1, we let's say if we have only one element in the array, or only one element, yeah, so probably just a sanity check for such cases. We never pass that, but yeah, just for, you know, like for arrays which are sorted, and it just happened that we execute this procedure onto them. If we are looking for the maximum, it's just a last element, so we just return nums minus 1, or len nums minus 1, because we need to return an index. Okay, cool. So this is the procedure to find a pivot. Let's call it def pivot, and we pass nums. Alright, so now we need to actually use this, and we also need to create a binary search, write a binary search algorithm which will call after we found a pivot. So the overall algorithm is first find a pivot, which is call pivot is equal to, or pivot idx is equal to pivot, and we pass nums. So this actually called it a grunt check, like 0 check, 1 check, and then the second step here is to call binary search. So if pivot okay, so actually let's do that. So now we have a notion of a target. So if our target, and now we need to like figure out so which part actually we will be searching on. So if our target lays here in the first part, how we can check that? We need to check to compare with the first element. Check that if target is greater than the first element, nums 0. So in that case, we do a binary search on the first part. We pass nums again. We pass our target, and we pass from 0 to the maximum, from 0 to the pivot idx. So it's now and we need to return that. So we return the result of this binary search. Okay, so this third case, if it's not the true, so if our target is not here in this first part, then it should lay somewhere here in the second part, right part, and we do this by returning results of binary search, nums target 0 to no 0. In this case, first element, the very first element will be pivot +1, and the last element will be len nums -1, the last element. Right, so let's recall what binary search is. Quickly write it down. So def nums target and LR, and we just look for while L is less than equal R. Take the middle element L plus R divided by 2, and then we check if our nums M is equal to target. We return M, else if or elif or if target is less than nums M, then we so let's visualize this. We have our M pointing to the center of the of this set of elements between L and R, and if first we checked if the middle central element is equal to target. If it is not, there are two cases. One is target lays to the left. In this case, we check is this equation inequality, and so what happens in this case? If that's true, if target is here, we need to continue looking at the left part. In this case, we just move our pointer here, so we make it R is equal to M -1, and the remaining cases where target lays to the right from the middle element. In that case, we need to move our left pointer just after our middle element here. So we put else put L is equal to M +1. Okay, so this happens until we reach the point where L is greater than R. So in that case, that means we didn't find our target element, and we just need to here return -1. We didn't find it, and that's it. In the one of the next video, I will make about the binary search in sorted rotated array with repeating elements, which will be different algorithm.